remotely, or I can record, I guess.
I think Manuel is recording.
Oh, okay.
Yes.
Okay, we're happy to have Maru Sarazola from Cornell University telling us about cotorsion pairs and a K-theory localization theorem.
Okay, so thanks, Jeremy, and thanks, Manuel, for the invitation to speak here. So what I want to tell you today is about this paper that I did as part of my thesis, which is, like the title says, on cotorsion pairs and a K-theory localization theorem. So the way that the talk is going to go is I'm going to spend a few minutes telling you about what is the problem that I was interested in. Then I'm going to give you a bit of a reminder on abelian, exact, and Waldhausen categories, because these are going to be the relevant structures that we're going to be working with. Then I'm going to introduce these words that appear in the title, which are cotorsion pairs. These are an algebraic kind of gadget. And then I'm going to tell you how we can obtain Waldhausen categories from cotorsion pairs and use these to get the localization theorem that I'm looking for. And hopefully we'll have time to see a few examples. All right, so what is the problem that I wanted to tackle? Well, this all starts with the fact that algebraic K-theory is a pretty hard thing to compute. And so for that reason, it's really useful to have results in the field that relate the K-theory groups of different categories. The idea here being, if you're interested in the K-theory of some category and you can't really compute it, but you can relate it to something else whose K-theory groups are more familiar, then you can try to leverage that information into something useful for you. So a major tool in this direction of relating different K-theory groups is that of finding homotopy fiber sequences. So if we manage to find a homotopy fiber sequence of K-theory spaces like this, why would this be useful? Well, we have our category, let's say our category A, and from it we can produce the K-theory space. Or if you are more stably inclined, let's say the K-theory spectrum. And from this topological space, or from this spectrum, we obtain the K-theory groups, which we just define as pi n of this space, right? So here we live on the land of abelian groups. So the idea is, if you manage to get a homotopy fiber sequence like this in the land of spaces, then this is very good for finding the K-theory groups of these things, because any such homotopy fiber sequence of spaces induces a long exact sequence on the K-theory groups. And then the idea is you just use this long exact sequence. Let's say if you know the K-theory groups of 2 of the 3 categories involved, you can try to figure out data about the third one. Okay. So among these results where we try to find homotopy fiber sequence, there's really not that many of these, but probably one of the most famous is Quillen's localization theorem. So what does this theorem say? It says, let A be a Serre subcategory of an abelian category B, where this Serre word is a condition on the short exact sequences. So the Serre word means whenever we have a short exact sequence like such in our category A, then if X and Z are in A, then the middle object also has to be an A. And then conversely, if the middle object of the short exact sequence is an A, then both of the other 2 objects have to be an A. So this means not only is it what we call closed by extension, meaning if we have the 2 endpoints, we have the middle one, but it's also closed by all possible subobjects and all possible quotients. So that's what this Serre word means, and you might be imagining that it's a bit restrictive. But if we have a Serre subcategory of an abelian category B, then there exists a quotient abelian category and a functor that acts like a projection to the quotient, which is universal. And these three categories, A, B, and the quotient, fit into a homotopy fiber sequence. So this is Quillen's localization theorem. So basically, it's telling us if we have an inclusion of categories where A is Serre, then you can find this cofiber category B over A that's going to fit in the cofiber spot of a homotopy fiber sequence. All right. So this is an awesome theorem, and it's turned out to be very useful for a bunch of applications. But the shortcoming is that it only applies to abelian categories. So this word abelian here is pretty important to get the theorem up and running. And the issue is that many of the categories that we care about in algebraic K-theory are not really abelian, but rather they are exact categories. So for example, one of the most important things perhaps that we care about is the K-theory of rings. And this is defined as the K-theory of the finally generated projective R modules, and that is just an exact category that is not abelian. So one would hope that you can find a version of this localization theorem that applies to exact categories. And in fact, that is true. So different authors have followed this line of thought and successfully generalized Quillen's localization theorem to exact categories. And the statement looks pretty much the same. We still start with an inclusion of two categories where now they are both exact. And the smaller category is still assumed to be Serre plus some other technical conditions. And if you assume that, then everything holds in the same way. So you still get a quotient category that's an exact category, and it fits into the homotopy fiber sequence. Okay, so that's great. That sounds like exactly what I wanted. It definitely allows for more applications because now we can use exact categories, but it still may be quite restrictive in practice. So let me tell you what I mean by that. So now we have a localization theorem that works for exact categories. And like I was saying, one of the very important exact categories is this proj, the category of projective R modules. So we might say, okay, now let's try to apply our localization theorem to proj. And what inclusion do we have that involves proj? Well, proj is included into all our modules. So we could take this as A and this as B, and that will be pretty great because the K-theory of proj is the K-theory of the ring, and the K-theory of our modules is what we call the G-theory of the ring. So both of these things are important invariants of the ring that we would like to be able to compute. So great, let's try to use the localization theorem to relate these two categories and try to figure out what the difference between those two K-theories is. However, when you go ahead and try to do that and try to check the conditions of the theorem, you will find that proj is pretty much never a Serre subcategory. So if you'll remember, one of the conditions of the Serre subcategory was that it contains all quotients. So think about it this way. Let's grab a random R module. We know that any R module is a quotient of a free module, right? And free modules are projective. So any R module is the quotient of a projective. So if projectives were closed under quotients with the Serre condition, we will be saying every R module is projective. So not only is the class of rings with that property very, very small, we're talking about like matrix rings or something like that. But furthermore, if we have a ring with this property, then by definition, this is an equality. And so K of R will be equal to G of R, and we don't really need the theorem anymore because the comparison that we want to study is really trivial. So we can only apply the theorem to study this when we don't need the theorem because we just have an equality. And that seems like a pity. So my goal is going to be to try to prove an exact version of the localization theorem that allows for a different type of subcategory that's not Serre. So this Serre condition is really killing us here a little bit. So I'm going to try to see if we can relax this Serre condition and try to get a similar result. So of course, as you can imagine, you can't just go ahead and wipe a condition from a theorem and expect it to hold, not even close. If you just dive into the proof and try to do that, you will find an immediate obstruction. So you immediately run into a wall because this property turns out to be vital for proving that this quotient category is an exact category. So if you still want it to be the kind of category that you're working with, you really can't get away with not having this Serre condition. So what is the workaround? Well, we're going to take a different approach. I apologize about the noise. I think there's a truck right down my window. Anyway. So we're going to take a different approach. Instead of trying to look for an exact category that fits into this co-fiber spot in the homotopy fiber sequence, since we can't have that without the Serre condition, we're going to say, well, exact categories are really not the only type of categories that admit a good K-theory machinery. So instead of striving for an exact co-fiber, we're going to try to construct a Waldhausen structure on the category B that's going to fit in the place of this co-fiber. And so instead of quotienting out by the things in A and making them trivial in this way, we're going to try to make them trivial by using the weak equivalences in our Waldhausen category. So we're going to try to build a co-fiber that's now Waldhausen, and that makes everything in A weakly equivalent to 0. Okay, so that was for the goal of my project. Now, since the type of structure that we have is quite relevant to the problem, let me just remind you a bit what the difference is between abelian and exact and Waldhausen categories. So abelian categories are categories that behave like categories of modules over a ring. And the important features that I want to highlight is every map has a kernel and a co-kernel, and we have short exact sequences. So importantly, what this means is whenever we have a monomorphism in an abelian category, let's call it I, since every map has a co-kernel, we can take the co-kernel of this monomorphism and complete the monomorphism to a short exact sequence. So pretty much every monomorphism can be completed to a short exact sequence. And similarly, every epimorphism, let's call it G, if we start with an epimorphism, since every map has a kernel, we can take its kernel and complete the data of the epimorphism to a short exact sequence. So we have all the short exact sequences that we could hope for. If you're not used to working with this type of category, really, you're not very far off from just keeping the category of abelian groups in your mind as a prototype example. So what are exact categories? What is the difference? Well, exact categories are going to be nicely behaved full subcategories of an abelian category. So now, since we have a subcategory of an abelian category, we're likely missing some objects. And that's going to mean that we're going to be missing some kernels and co-kernels likely of maps. So this results in us having a restricted class of short exact sequences. And the prototype example to keep in mind here, like I mentioned before, will be, for example, the category of projective modules over a ring. So why, maybe it could be a bit enlightening to see why is the category of projective modules an exact category and not an abelian one? Well, if we take, for example, the ring to be the integers, and we consider the map from z to z that just multiplies by 2. This is clearly an injection, so this is a monomorphism. What happens when we take the co-kernel of this? Well, the quotient is just going to be z mod 2z. And what happens here is that z is a projective z module because it's free. However, z mod 2z is not a projective module. So this is an example of a co-kernel in the category of projective modules. Of a monomorphism in the category of projective modules whose co-kernel does not live in the category anymore. So we would say that this short exact sequence is not allowed because it doesn't live in our category. So this is what I mean when I say we have a restricted class of short exact sequences. Some are going to still be there, but some are probably not going to be there anymore. So the monos, or respectively epis, that do have a co-kernel or a kernel in our category are going to be the nice ones. And these are going to be the ones that we're going to want to consider, and we call them admissible. So although it may seem minor, having more or fewer short exact sequences actually makes a big impact on the K-theory of these things. And let me explain briefly why that is. So if we look at K0, what is K0 of an exact category? This is going to be just the growth in the group. So this is the abelian group generated by the set that takes one representative for each object in the category. So we take that set and we generate a group, we generate an abelian group, and to what we get, we apply an equivalence relation. So how is this equivalence relation defined? Well, we say for any short exact sequence in our category, we are going to induce the relation that the class of the middle thing, the class of y, is equal to the class of x plus the class of z. So we see that the short exact sequences that we have are going to impact K0 in that they tell us exactly how we can decompose the objects in K0. So it really makes a difference if you have them all or if you only have a few. All right. So finally, what are Waldhausen categories? These are going to be a different type of structure. These are pointed categories, so we have a zero object, together with two distinguished classes of maps, which we call cofibrations and weak equivalents, that of course have to satisfy a list of axioms. So instead of listing the axioms, which will be a bit long and boring, allow me to give you an idea of how these classes of maps behave by showing you the effect they have on K0, just like we did with the exact category case. So again, K0 of a Waldhausen category is defined in a similar way. So this is going to be the abelian group generated by the same set. So we take one representative for each object in our category, and we mod that out. But how do we define this relation now? We don't have short exact sequences necessarily, because I'm not saying that these have to be algebraic structures of any kind. But we do have these classes of morphisms, and these are going to give us the relations. So first we have cofibrations, and the cofibrations are going to behave like the monomorphisms did in the abelian and exact categories. So for any cofibration like tell us that we must be able to take this push out to the zero object. So if we find the push out, we are going to induce the relation that the class of y is the class of x plus the class of the push out. So much like in the abelian and exact case, the cofibrations tell us how we can split up our objects in K0. But now we have the additional data of weak equivalences, and these, just like every time we have weak equivalences, are going to teach us how to glue things together. So whenever we have a weak equivalence between two objects, we're going to impose the relation that those two objects need to have the same class. So we can see that abelian and exact categories are really algebraic inputs for K-theory, because you can only see their algebraic structure through the short exact sequences. But Waldhausen categories instead are of a more homotopical nature, because now we can identify things using the weak equivalences. So an example, perhaps you're wondering what the relation between these different types of structures is. Well, exact and similarly abelian categories can be seen as Waldhausen categories by taking cofibrations to be the nice monomorphisms and by taking weak equivalences to be isomorphisms. So in this case, we wouldn't want to be gluing anything that's really not the same. So we're not including any extra homotopical information here. But perhaps an example more representative of the spirit of a Waldhausen category, even keeping some algebraic nature in the background, is that of chain complexes. So chain complexes are a Waldhausen category when we take cofibration to be the degree-wise injections and weak equivalences to be the quasi-isomorphisms. All right, so before I move on, this is probably a good time to pause for questions. All right, so let me do a small recap of what we wanted to do. We wanted to start with an inclusion of two exact categories, A inside of B, and we wanted to construct a Waldhausen category to act as the cofiber that's going to make everything in A weakly equivalent to 0.
Sorry, can I ask a question? It's a little late, but
yes, of course.
So I hear that there are these generalizations. You go from abelian to exact to Waldhausen categories. If you start from an abelian category, or if you start from one stage and go consider the things that you have as the objects in the next stage, do the K-theories always match?
Yes, absolutely. So abelian and exact categories have the same K-theory machinery, so those are going to match trivially. That's what people usually call the Q construction. And Waldhausen categories have a different K-theory machinery, which is called the S-dot construction, but they both produce the same space. So if we have an abelian or an exact category, it doesn't really matter if we want to look at them as exact, or if we want to consider the isos as weak equivalences and look at them as Waldhausen, because for K-theory purposes, they're going to produce the same spaces.
Thank you.
Thank you for that.
Thanks.
All right. So we were saying our goal is to construct this Waldhausen category to act as the cofiber, and the tool to do that is going to be that of Cotorsion pairs. So what are these things? Well, in abelian, just like in abelian categories, whenever we have an exact category, we can construct the unetta bifunctor x1. So remember, x1 of A comma B is going to be the equivalence classes of extensions like this, having B, C, and A. So we're probably used to doing this in categories of modules. We can do that in abelian categories in the same way. And furthermore, since we still have some short exact sequences in an exact category, we can still define this x1 functor in the same manner. Now we're going to have just fewer of these, but that's fine. All the definitions and properties go through in exactly the same way. So using this x1 functor, we can define Cotorsion pairs in an exact category. So these are going to be pairs of two classes of objects in our exact category that are the orthogonal complement of each other with respect to the x1 functor. So what does that mean exactly? Well, an object P is going to belong to the class P if and only if, when you take the x of P and anything in the class I, it vanishes. So you get 0 for every I in I. So note that we're saying that the things in P have to make all the things in I vanish. But since this is an if and only if, we're also saying anything that makes all the things in I vanish has to be in P. So there's a maximality condition hidden here. And similarly, something belongs to the class I if and only if it makes everything in the class P vanish when we apply the x1 functor.
Can I quickly ask, so 0 probably means that there is the trivia extension, so exact categories always have like a direct product or
yes, exact categories always need to have this extension.
Great, thanks.
Yeah. So I was sweeping this under the rug when saying exact categories are nicely behaved subcategories of abelian categories, and this is one of the nicely behaved properties. Yes. So what is the example to keep in mind when we're talking about Cotorsion pairs? It's that of injective and projective objects. So indeed, if we just take the classical projective objects in a category of our modules, we see that an object is projective precisely if the functor hom out of P is an exact functor. And that's going to happen if and only if x1 out of P is 0. So x1 PA vanishes for every A in our exact category. So note that this is exactly saying that if we take the pair where the first class is that of projective objects and the second class is the entire class of objects, then this is going to be a Cotorsion pair. And similarly, if we take all objects in the first class and injective objects in the second class, that is also going to be a Cotorsion pairs. So these two are Cotorsion pairs no matter what our exact category is. And not only are injective and projective objects examples of Cotorsion pairs, but Cotorsion pairs were born to generalize injective and projective objects. So the idea is that in a Cotorsion pair, we have two classes P and I, and now the objects of P are going to be projective relative to those of I. And the ones in I are going to be injective relative to P. So Cotorsion pairs are a way for us to do relative homological algebra. And just like in the typical case of projectives and injectives, we can still interpret these conditions through a lifting. So for example, if we look at the condition on the class P, we see that an object P makes everything in the class I vanish exactly if for every map from P to any object Y and any epi G to Y, like in the picture, whose kernel is in the class I, we need to have a lift like that from P to X. So the classical notion wouldn't require this part in here because we would be working with this Cotorsion pair with I is the entire exact category. So we would just be saying for any nice epi, for any epi whose kernel lives in our category, this has to be true. Okay, so at this point, we have this notion of Cotorsion pairs, and we've just seen that they can be defined in terms of lifting conditions. And in fact, these can be related to the lifting conditions that we can find in a model category. So Javi studied the relation between Cotorsion pairs and model categories. And he has this really neat theorem saying that if we fix an abelian category A, then we have a one-to-one correspondence between pairs of Cotorsion pairs and abelian model structures one can define on our category A. So an abelian model structure is one where the cofibrations and fibrations still see the algebraic structure in A in a very precise manner. And Javi showed that these are in correspondence to pairs of Cotorsion pairs. So note that these are not just any two Cotorsion pairs, because there's only 3 classes involved. So they have to be pairs that are compatible in this way. And the idea here is that this class C is going to be the class of cofibrant objects in our abelian categories, in our model categories. And the class F is going to be the class of fibrant objects in the model category, and the class Z is going to be that of acyclic objects. So the ones weakly equivalent to 0. Okay, so starting from a model category, we can take these classes and prove that they form Cotorsion pairs, but more interestingly, we only need these pairs of Cotorsion pairs to define all the structure in a model category. So inspired by this result, what we're going to do is study the relation between Cotorsion pairs and Waldhausen categories instead. So the question here is, so for model categories, we really do need these 2 compatible Cotorsion pairs, because what's going to happen is each of these Cotorsion pairs is going to play the role of defining one of the factorization systems that we need to have present in the model category. But what if we really only care about algebraic K-theory? And in that case, we don't really need a model structure. We can make do perfectly fine with a Waldhausen category. So can we maybe, if we are scrapping the fibration side of the model structure, can we maybe just make do with 1 Cotorsion pair to determine the entire Waldhausen structure? And what we're going to see is that the answer is basically yes. So our main result explains how we can produce a Waldhausen category structure from a Cotorsion pair together with a chosen subcategory, which is going to act as the acyclic objects. So you have a Cotorsion pair, you wonder, okay, who would I want to kill in K-theory? That's going to be your class Z. And subject to some conditions, this gives a machinery that spits out the correct Waldhausen category. So here is the result. If we have an exact category E and 2 subcategories C and Z of our exact category having the following properties. So we need Z, which is going to be the class of acyclics, to be closed under extensions. Remember, this was the property that if in a short exact sequence we have the 2 endpoints, then we have the middle point. And also closed under co-kernels of monomorphisms. This one tells us if we have a monomorphism between things in C and Z, then the co-kernel also has to live in Z. And now for conditions on C, we ask that it be a part of a complete Cotorsion pair. So first of all, let me note that whenever you have an exact category or subcategory C, you can always take C perp like we're doing right here. So you can just define C perp to be the objects in your ambient category such that X1 of Cx is 0 for every C and C. So you can take the orthogonal complement of C. That's something that you can always do. but there's no guarantee that this will form a Cotorsion pair, because remember we have this maximality condition, and there's really no guarantee that the perp of the perp will be C. It could be something bigger. But now we're saying assume that our class C is part of such a Cotorsion pair, and we want this pair to be complete, and this adjective is basically saying that we want to have enough injectives and projectives. And now if this perp is contained in the class that we want to have as our trivial objects, then the result says that the category C admits a Waldhausen structure, which is constructed in the following way. So I need to tell you who the distinguished classes are. And we're going to set cofibrations to still be the admissible monomorphisms, because we do have an algebraic underlying structure in C, and we don't really want to change that completely. So we want to keep the short exact sequences and the splittings to be given by the algebraic data, just like we would if we just consider C as an exact category. But now we want to add a class of weak equivalences, and these are going to be defined as the maps. So a map like this is a weak equivalence, precisely if we can factor it as a mono with a trivial co-kernel followed by an epi with trivial kernel. And this is going to be our class of weak equivalences. So of course, in order to prove this theorem, one has to grab these classes and check off all the axioms of Waldhausen categories. And it's not a trivial thing to do, in the sense that, so imagine if you're familiar with, if you're used to working with model categories, imagine you grabbing two factorization systems. So you have a notion of trivial cofibration and a notion of trivial fibration, and then saying, okay, let's define the weak equivalences as the maps that factor as a trivial cofibration followed by a trivial fibration. So of course, you know, if you're going to have a model structure, all weak equivalences need to have that property. But now we were saying, let's define them through the property, and then cross our fingers and hope that this gives us a compatible class of weak equivalences that actually give a model structure. That would not be a trivial thing to prove. And similarly, it's not trivial to show that these are well-behaved weak equivalences in the Waldhausen axioms. And if you're familiar with those axioms, let me quickly name that the hard part is proving what we call the gluing lemma. And there's some fun ideas that go into that, but maybe I can tell you later if someone is really interested in this. Okay, so now we have this machinery that, given a Cotorsion pair in a class of acyclics, spits out a Waldhausen category collapsing all those acyclics. Let's try to see, for example, if we can use this machinery to construct the Waldhausen structure on chain complexes that we were talking about earlier. All right, so if we want to construct the Waldhausen structure on chain complexes, then some of these categories are already pretty much given to us. So C is going to be chain complexes, because C is the place where we define the Waldhausen category in the theorem. And so since C is the entire category already, it's going to be equal to E. And now we need to determine our class Z. So remember, these are going to be the things weakly equivalent to 0. But if we want to recover the usual Waldhausen structure on chain complexes, this one had quasi-isos as the weak equivalences. So Z has to be the chain complexes which are quasi-isomorphic to 0. In other words, the exact complexes. So now the relevant classes are already determined, and we just need to prove that they satisfy all the conditions. So first of all, why is C part of a complete Cotorsion pair? Well, if we have the entire category now as the first class, remember we said we can always take the injective objects, and no matter what the exact category is, entire category, comma, injective objects is always a Cotorsion pair. So that's fine. And being complete, like we said, is having enough injectives. So that is also fine for chain complexes of modules. And now for the other conditions, one can prove that exact complexes are closed under extensions and co-kernels of monomorphisms. One can actually prove more, because if you have a short exact sequence of chain complexes, you can prove that if any two of those objects are exact, then the third one is going to be exact as well. So we actually can prove something stronger than what we need in this case. We can also prove, sorry.
Can I ask one question?
Of course.
Injective chain complex is the same as chain complex of injectives?
They are not, unfortunately. So chain complexes, injective chain complexes do need to have each degree injective, but they need to satisfy some extra conditions. Yeah, they're a bit of a pain to pin down, but that condition is exactly what's going to give us one of the other axioms that we need, which is that injective chain complexes need to be exact. So not only degree-wise injective, but they also need to be exact.
Thank you.
Okay, so these are things that if you just pull up your sleeves and work with the chain complexes, you can prove. And this already means we can use our theorem. We can run this Cotorsion pair in a cyclic class through our machinery to get a Waldhausen structure on chain complexes, having the cofibrations as the degree-wise monomorphisms, and having as the weak equivalences these maps that factor as degree-wise monomorphisms with exact co-kernel, followed by degree-wise epimorphisms with exact kernel. But in fact, one can prove that that factorization condition determines exactly the class of quasi-isomorphisms. So a map is a quasi-iso if and only if it factors precisely in this way. So we see that the Waldhausen structure that we're getting through the theorem is recovering exactly the classical Waldhausen structure on chain complexes, now built from this data of the Cotorsion pair. Okay, so for a last word about these categories constructed from Cotorsion pair, they have really nice properties. So these are going to relax the notion of exactness, but they still exhibit a very strong algebraic nature. And as a consequence, they are very, very structured and well-behaved. So for example, they are proper. They satisfy what we call the extension axiom in K-theory. We have the property that we don't usually have in Waldhausen categories, that every map factors as a cofibration followed by a weak equivalence. This is because, remember, Javi proved that two Cotorsion pairs give you a model structure, because from each of those you can determine a factorization system. Now we're only keeping one of those, so we still keep one factorization system in our category. That's what gives us this really nice property. We also have an explicit description by definition of the weak equivalences in terms of kernels and co-kernels. So even the weak equivalences, which bring the homotopical part to the table, still behave kind of in an algebraic way through their definition. We can prove that the acyclic objects are precisely the objects of our chosen class Z. So something is such that 0 to x is a weak equivalence if and only if the object is in the class Z. And lastly, we can pin down when we have 2 out of 3 for weak equivalences. And this is going to happen when the class Z has the missing condition for having 2 out of 3 for short exact sequences. So we said if we have a short exact sequence, our theorem requires If you have the two endpoints, you have the middle. If you have the two leftmost, you have the rightmost. But we're saying if in addition to that, you have the other missing property, then you're going to have 2 out of 3 for short exact sequences. So we're going to see how all these nice properties come into play now when we try to leverage this theorem to get our localization result. So remember, the end game of all this was to be able to start from an inclusion of 2 exact categories, somehow relax the Serre condition, and manage to construct a cofiber using a Waldhausen category that fits into a homotopy fiber sequence of K-theory spaces. So let's see exactly what that's going to look like. So the statement of the theorem is now going to be, let B be an exact category with enough injectives, and take a full subcategory A having 2 out of 3 for short exact sequences and containing all injectives. So let me quickly remark the difference between these conditions and the classical ones. First of all, here we're talking about injectives, which we weren't doing at all before. That's because now we're going to be talking about Cotorsion pairs. So we do need some condition to make the Cotorsion pairs behave well. But we are also weakening the Serre condition. So remember, the Serre condition was whenever we have a short exact sequence, we said if X and Z are in A, then Y is in A. And we said if Y is in A, then both X and Z are in A. So we're saying it's closed by extensions, but also it needs to have any subobject and any quotient of an object in A. Now we're relaxing that with this 2 out of 3 property for short exact sequences. So part of that is going to be the same closed by extensions property, but now we're saying if X and Y are in A, then Z is in A. And if Y and Z are in A, then X is in A. So we don't need to be closed by all possible subobjects. We just need to have those subobjects whose quotient we know is in the category. And similarly, we don't need to have all possible quotients. We only need to have quotients by subobjects that are also in the category. So this is exactly how we are relaxing that very strong Serre condition. Now, if we have all these properties, then the claim is that there exists a Waldhausen structure on the category B, having admissible monos as cofibrations, because like we said, we wouldn't really want to change those, and fitting as the cofiber on a homotopy fiber sequence involving A and B. So let me give you a sketch of how this result is proven. And we're going to see that really most of the heavy lifting is going to be done by our previous theorem, the one that gives us a machine for producing these Waldhausen categories. So I'm just going to copy the statement of the previous theorem right here. And what we're going to do is we're going to determine who the relevant classes need to be. So our theorem builds a Waldhausen structure on the category C. So that tells us that C is going to be B for us, because that's where we want to define the Waldhausen structure. And we're going to let the ambient exact category be B as well. And then for the trivial class, we said we want our Waldhausen structure to make everything in A weakly equivalent to 0. So we're going to take A as our class of acyclics. And now let's see if we can check off quickly the conditions of the second theorem. So we needed the class of acyclics to be closed under extensions and cokernels of monos, but we're going to have that and more because A has 2 out of 3 for short exact sequences. So in particular, those will be 2 out of the 3 conditions of the 2 out of 3. So we're good on that part. Now we also need C to be part of a Cotorsion pair, but we said whenever we have the full category as the first class, we can always take the injective objects, and that's going to be a Cotorsion pair. So that is good. And the complete part was having enough injectives, which we are requiring right here. So finally, we need the perp of our category to be included into the acyclics, but the perp are the injectives. And that's why we ask that the category A contains all injectives. So we can run the machinery and obtain a Waldhausen structure on B, having exactly the cofibrations that we wanted to have. So we just apply the previous theorem and construct a Waldhausen category, which we denote in this way from the Cotorsion pair B and injectives. So now we have our Waldhausen category. Why does it give us the desired homotopy fiber sequence? Well, that is a bit trickier, but one can see that because we have such nice properties, we can use those properties to prove the homotopy fiber sequence. So the extension property that we have combined with 2 out of 3 for weak equivalences, and with the fact that we have factorizations of every map as a cofibration followed by a weak equivalence, all these properties allow us to apply Schlichten's cylinder-free version of the Waldhausen fibration theorem. And that allows us to get a homotopy fiber sequence like this. So on the cofiber spot, we have our Waldhausen category. On the middle spot, we have the same underlying category, only now with isomorphisms instead of the weak equivalences. And on the fiber part, Waldhausen's fibration theorem puts this BW category, which in the statement of Waldhausen's fibration theorem, it's defined exactly as the elements in B, as the objects in B, such that 0 to X is a weak equivalence in the Waldhausen category. However, like we said, we constructed this Waldhausen category so that the class of objects that are weakly equivalent to 0 are precisely the ones in A. So we constructed this in a smart way so that this BW is exactly A. And like we were saying when Mahmoud was asking at the beginning of the talk, when we just say KB isos, we're looking at the exact category as a Waldhausen category, but this is the same as just saying KB when we look at it as an exact category. So in fact, this homotopy fiber sequence is precisely the one involving the K theory of A and the K theory of B, having a Waldhausen category in the cofiber spot. So this is how we obtain the homotopy fiber sequence that we wanted. So to say some final words, our construction, like we said, allows you to, starting from a category in a chosen class of acyclics, spit out a Waldhausen category that has all these nice properties and fits into the homotopy fiber sequence, but it's actually optimal in a very precise sense. So we can show that our construction is universal in the following sense. So if we have all these conditions, then we can always take the identity functor from B to our Waldhausen category because they still have the same underlying category. And we can see that this identity functor is going to be universal among exact functors from B to any other Waldhausen category C, having the extension property and the 2 out of 3 property for weak equivalences, that makes everything in A vanish up to weak equivalence. So if we manage to find some other Waldhausen category with these nice properties, and with the property that everything that comes from A inside of B is weakly equivalent to 0. So if we manage to find that, here we have the identity into the one that we constructed, then actually one can prove that the construction, the functor f, has to factor through our Waldhausen category. So in a sense, this is the smallest such Waldhausen category in this very precise manner. All right, so maybe to wrap up, let me quickly show you a few examples. So like we said, we can use this Cotorsion pair machinery to recover familiar Waldhausen categories, like the one for chain complexes and quasi-isos that we saw a bit earlier. But maybe more interestingly, we can also produce new stuff. So since our theorem now doesn't have the Serre condition, but rather a new set of constraints, we can use our new localization theorem to compare K of R and G of R, at least for certain classes of rings. Remember, this is what we could never do before unless the comparison was trivial. So for example, if we let R be what we call quasi-Frobenius rings, these are rings where the projectives and injective modules are the same, then we can take the trivial class to be the projective injectives. And this, it's quite easy to show that does satisfy 2 out of 3 for exact sequences. And so we can apply our theorem to get a Waldhausen structure on our modules, having cofibrations as the monomorphisms and having these projective injective modules as the trivial ones. And now if we apply our localization theorem, we obtain a homotopy fiber sequence like that, where we have K of R, which was K of Proch. This is the K of A part in our localization theorem. We have K of R mod, which by definition is G of R. And on the cofibers part, we have this new category that we constructed. So in a way, we're saying that the key theory of this Waldhausen category is going to come here to measure the difference between K of R and G of R for these classes of rings. So some quasi-Frobenius rings that we might care about are Z mod NZ for any n, KG for any field and finite group, or any finite dimensional Hopf algebra. All these are examples of quasi-Frobenius rings. And then finally, for a more maybe geometrically flavored example, if we take a ring that is an Artin algebra in a Gorenstein ring, and we take its class of maximal Cohen-Macaulay modules, then one can show that all the conditions of localization theorem hold, and that we get a homotopy fiber sequence relating the K theory of Proch, which as we know is K of R, and the K theory of the category of maximal Cohen-Macaulay modules by this new cofiber. But an interesting fact for these rings is that every R module admits a finite resolution by maximal Cohen-Macaulay modules. So that means that we can use Quillen's resolution theorem to compute K of R modules as K of the Cohen-Macaulay modules, just because we have these resolutions. And so again, this homotopy fiber sequence is again measuring the difference between K of R and G of R by this new constructed cofiber. Okay, that's all that I wanted to tell you today. Thank you so much for your time.
Are there any questions?
I have a few very naive questions. First off, if could you take just inj? Is that in just the injective modules? Would that satisfy 2 out of 3, and all of those things? Could you take the K-theory of that and put it in your machinery?
Right. That is a good question. So remember, like we said, when we take proj, we had this example of this monomorphism whose co-kernel was not in proj anymore. So this proves that proj doesn't have co-kernels of monomorphisms. Dually, you can prove that in general, Ing doesn't have kernels of epimorphisms. I don't really have an example in mind right now, but that in general, if you take just any random ring, that's going to be, so injectives are closed under extensions. They are closed under co-kernels of monos, but they won't be closed under kernels of epis. That's why this example here, when a ring is quasi-Frobenius, works so well, because in this case, the projectives and injectives are the same class. So the projectives are going to bring us the kernels, because they always have the property, and the injective part is going to give us the co-kernel. And so we combine them together 2 out of 3. But in general, injectives will not have 2 out of 3.
I see. I think that also already answers all the other naive questions that I had after that. Great, thanks.
Hi. I also have a few questions. It was a very nice talk. Thank you. How are Waldhausen categories organized and compare in general? For example, is there a good notion of a weak equivalence between Waldhausen structures? Is there a homotopy theory for these? Is this something that has been studied? And
Not that I know of, honestly. We do care about like which functors between Waldhausen categories give you the same, like induce this like homotopy equivalence on K theories. Mm-hmm. But that's actually quite a hard question. So just like there's these homotopy fiber sequence theorems trying to relate the K theory of A and B, there are a few theorems trying to tell you when a functor is going to give you a homotopy equivalence on K theory. But there's really very few of those. And the conditions are, they're pretty hard. It's not at all well understood when such a thing will happen.
I see. Yeah. So
for example, just like to give you an example, one theorem that we use a lot in K theory to get that is Quillen's theorem A, which tells you like if you have a functor between 2 categories and some conditions are satisfied by the comma categories, then you have a homotopy equivalence of the spaces of the nerves of the categories. So we use that a lot when we do K theory of exact categories by doing the Q construction, and then we try to get when the comma categories of the Q construction have this property.
Right.
But of course, this isn't a tight result in any way, right? Because it's really not an if and only if, like by a mile. So we have these kind of results that we try to approximate, but it's not well understood when exactly this happens. As far as I know, there's no like model structure of Waldhausen categories or something like that.
Okay. I'm going to stop the recording just in case anyone wants to ask questions.